Okay. Okay, everybody, you are in for a treat. Okay, so let me introduce Carmen. So Carmen, first of all, you have to know that she grew up in Spain, right?
Yes.
Okay, and she, came from a town, a hiking town, a town where you can go hiking, even though she doesn't like to hike. What a waste I am. I'm a hiker. But she went to Madrid to major in college, to major in aeronautical engineering. And I asked her why airplanes. And she said she was just curious about how you can get this incredibly heavy machine off the ground, right? I mean, it's a mystery. But she came at it from a different perspective. She came at it from a mathematical perspective. But you know, a mathematical engineering, mathematically oriented engineering perspective, which of course is all about control theory. So you were already, heading in that direction. So how did she get to Caltech? Right, she did her PhD at Caltech with John, right? You know that. Well, she took a summer internship, which was at JPL in their space division. And she did so well, or she liked it so much, that she stayed on to do a master's degree in aeronautical engineering.
Yeah.
Okay. And I don't know anything about aeronautical engineering at Caltech, but I presume that's a pretty good operation, right? I mean, it's what? Phenomenal. Okay. However, the turning point in her life was a lecture she heard in a course that was given by John on robust control theory. She said it was the coolest thing ever. And that is really says something about John, and also that you have very good taste. And however, okay, this also tells us something about her. Okay, is that and John alluded to this, that it turns out that her father is a linguist, and so she from a very early age was curious about language, and always had this in the back of her mind that this is something she wanted to pursue. And so here she is, she's halfway through her PhD, and she's doing great. What the PhD, it was going to win her this big prize at Caltech, the Positive Prize.
Bunches of prizes.
Okay, in addition to all the other prizes.
Yeah, bunches of prizes.
Okay, so this is a prize-winning kind of.
Which we'll talk about on Monday.
Yeah. By the way, just before I forget, there's going to be another talk on Monday in the very same room at 3:30 on SLS, system level synthesis, and it's what John was talking about. But now we're going to dig down into the machinery and see how it works. It's been you'll see it's a way of doing distributed computing, which has been an open problem in control theory for many not Okay, so she decided she would actually go back and try to take another look at language. Not another look, but follow her interest, her passion for language. And she said that John warned her away. Said that it's a complete mess. It's a quagmire, that there's competing factions that don't make any very ad hoc and so forth. And he must have thrown every pejorative at her.
It's not the worst feeling I've seen.
But it just slid right off of her. She wasn't going to take that as a reasoned argument. But in any case, for 2 years, and she finally decided. And this was the turning point for John. She discovered a book by Ray Jackendoff, who's a linguist, but it turns out that he actually had some good ideas that are relevant and resonated with John. And so that was now the beginning of the second phase in her career, which is trying to understand language from the perspective of control theory. Now, this is something that it would be very interesting. This may turn out, okay, at this this is the beginning of, I think, a new way of looking at language, but it potentially could help us understand one of the most complex things that humans do, which is communicate with each other and cooperate with each other. And the neat thing about it is that we learn it. Babies learn it. They just pick it up like this. How is that possible? And Chomsky's view was that it's got to be innate. You can't learn something as complex as language, but actually it may turn out that within this framework of the universal layered architecture, it may be that this is the most learnable of the architectures. And so I'm really looking forward to hearing more from Carmen.
Thank you so much, Terry. Thank you, Terry. That was really generous. Thank you, everyone, for coming here. I'm very excited to be talking to you about natural language and control theory. It's the first time I give this talk, so any feedback is very welcome. But if you were here yesterday, maybe you know that I was tasked with explaining to you the architecture of language. So I'm going to try to use the ideas that were discussed yesterday and tell you how those apply to language. So I made my slides Wall-E theme, so I chose this word, Wall-E. And if you've watched the movie, you're probably thinking of this character. If you haven't watched the movie, it's kind of fun. It's about what happens when architecture doesn't work, when we just mess up our architecture and then the earth is full of trash and this poor robot has to pick it up and we have to go live in space. But anyway, if you've watched this movie, you're probably thinking about the robot, and that would be the semantic layer of this word. You can think of this as projection. So this would be the semantic layer, but if you never heard this word, you're probably wondering how you pronounce it. And that would be the phonemic layer. So that tells us about how to put this, how to string the phonemes together to make up that word. And this word has yet another layer, which is the syntactic layer. And in this case, this is a noun and it's singular, and we can say things about its syntax too. And the cool thing about language is that we can make sentences with words. So I could say something like this. I could say, Wally says hi. And now the word says also has all these different layers to it. So it has a meaning, it has like some phonetics of how we pronounce it, and it also has some syntax. In this case, it's a verb, it's a third person. And the word hi is the same story. It's an interjection syntactically, it has some way of pronouncing it, and it has some meaning to it. But what's very interesting about language is that this very sentence has the same layers. So the sentence has some meaning that's not necessarily the combination of those three meanings, it's something else. It also has some phonetics to it, and it's not just stringing the words after each other, because sentences have some intonation and so on, and it also has some syntax to it in the way we put the words together. So we have here, alluding to the notation from yesterday, we have the word level, but we also have the sentence level, and they both have layers. So let me put that all into one picture. So this could be the architecture of language. We have the different layers, and we also have the different levels. So for the levels, we would have syllables, which make up words, which make up sentences, which make up paragraphs. And each of those levels have layers. So it looks something like this. And I really want to point out here that the layers for each of those levels are the same. So paragraphs have semantic syntax and phonology, sentences have semantic syntax and phonology, words have semantic syntax and phonology. That's unique for architectures. Most architectures that were discussed yesterday don't have these features, and most levels just happen to have different layers. So this is very unique to language, and we could conjecture that this is one of the reasons why language is so learnable by both babies and LLMs. But that's a conjecture. And so I had drawn this as projections. I thought it was like a nice way of thinking about it. But we could also think about this as an hourglass. So syntax is simple in languages. Once you can study the syntax at school, and it's a finite number of rules that you need to construct a language. But the number of sounds that you can make, it's pretty large. And then the amount, like the number of the different number, like the different meanings that you can have is probably like infinite. So that's, we have the hourglass here in the layers. And we also have bow ties. And the bow ties, here I chose this LLM notation because a lot of the talk is going to go around LLMs, but we take sequences. The amount of sequences that we have is much larger than the amount of tokens that we have in a dictionary or in an embedding space. And then we string those tokens together to make sequences, and we can make almost infinite amount of sequences. But in order for that to be meaningful, that needs to obey the rules of phonology, syntax, and semantics. So when we go through this bow tie, we have to, like, they happen in the levels, but at the layers, like all of the layers are involved in making this bow tie language appropriate. And we use these bow ties to build from words, sentences, paragraphs, etc. And this is what we call stages. So this is we have to, like, this is a very careful control process, because if you think about it, there is, if I take all of the words, like if I just take random words and put them together, that's not going to be a sentence. If I take all of the like random letters and put them together, that's not going to be a word. So this has to be a very careful selection in order for this to lead to something that's phonological, syntactically, and semantically appropriate. So so this stage is it's a careful control process. We're going to talk about that. And of course, this all happens obeying laws of both the brain, if like this is human speakers, or technology, like this happens in GPU or something, if this is an LLM. So all of these elements we think are important in the architecture of language, and we're going to discuss today in different works. So that's it for architectures. Now let me tell you how language and control theory can interface, and how this view of architecture is influential for making all of this works happen. So I thought, in case there's not a lot of control theorists in the room, I could address this question of what control theory is. And let's assume that we have a lot of different systems. Control theory is useful for all of them. So for the power network, for the solar system, for the automobile industry, for irrigation systems. And the reason why control theory is useful is because we can think of all the systems as a dynamical system. So what a dynamical system really is just a system that has a property that evolves over time. And in the case of this irrigation system, for instance, we want this evolution to follow some agenda that we might have. And in this case, we want it to behave optimally in this way, which is we want to minimize the cost. This is the amount of water that we are using, and also the amount of energy that we need to move the gates. And we want to do that by staying within the constraints. So we don't want the amount of water to be so low that it doesn't get to water this plant, but not so high that it overflows. And so in control theory, we do this with a controller. So this would be another dynamical system that we append to the original dynamical system, and it measures the water level in this case, and it tells us how we should actuate these gates. And it does that by minimizing the cost and staying within the constraints. And mathematically, we write that in this way. So we say this is the cost, and that is encoding the fact that we want to minimize the amount of water and the energy that we're spending in moving the gates. We are constraining this to the dynamics of the plant. So this is the evolution of the water level. And we also want to encode here the constraints that we don't want the water to overflow, for instance. So this is a typical control problem. And this is the kind of control problems that you're going to see throughout the talk when we talk about language. So now let me tell you about language and control and how they can interface. And I think they can interface in two ways. So one way in which I think they can interface is using language to control. So how can we use language to influence others? And in this case, how can we use language to influence technology in other? So how can we use language to control robots? So here's where this architectural view is helpful, because if we think that we have this hourglass or phonology, syntax, and semantics, we can think of this architecture as like a baseline to run things on top. And what I mean by that is we can say many things with language, and we can use language for communicating other things, meaning we can use language as a platform to, for instance, try to control this robot. So I could use language to put together a sentence that's phonologically correct, syntactically correct, and meaningful, and that is conveying a control command to this robot. And this robot has to somehow understand language too, to be able to decode whatever I said and execute that command. So this is, so I'll tell you how we can do that. But also there's this other dimension of how control and language can interact, because when we generate language, it's a bow tie. So it's this process where in particular in an LLM, we take a sequence, we choose the next token, we string it to the sequence, and we keep on doing this. So it's this very careful control process. And this is something that we can also understand and improve with controllers pretty explicitly. And we have to take into account the laws, which in this case would be the constraints that the hardware implementation give us to make this possible. So let me tell you about the first part of the talk, language to control. So how can we use language to communicate with robots? And you can imagine a world in which this is what we want. We want robots to communicate with humans. We want them to help us with everyday tasks, and we want them to be flexible and adaptable. However, this is the kind of robot that we have today. So there is no human around. In fact, there is this barrier that prevents humans from getting close to the robot. They're single purpose, and they have this hard-coded functionality. So what can we do about that? If we take this robot, the way robots usually operate is with a controller. And we've just talked about how we use controllers to control dynamical systems. In this case, the dynamical system is the robot. And so the controller sends signals to the little motors in the joints of this robot. And so that's why the robot can move. But it needs some expertise to be able to write down this math so that the robot does whatever I want it to do. And so we encode in the task, and we encode in the constraints the other things that we don't want to happen, so safety, like collision avoidance and this sort of thing. And in this paper, we explored this idea of, well, what happens if I just want to talk to my robot? I'm this girl that's not trained in control theory, so how do I tell my robot, how do I manage to get my robot to do what I want without needing to write down this math? And this is an architectural question, because I have this meaning in my head that I built up in this language hourglass, right? So that has its own phonetics and syntax, but it has also the semantics of I want you to build a pyramid, and I have to convey that meaning to the robot. Now, what's important to note here is that it's possible in math with a sequence of movements to capture that meaning, but the rest of the architecture is not quite the same, because math has a different syntax, and we could say a different phonology or different elements that have to come together to make that happen. So how do we bridge that? That was kind of the main question. And we, to solve this question, we use language models. Because language models just happen to be very convenient, if we look at the levels, they just work with tokens and sequences. So if you talk to ChatGPT, ChatGPT is gonna write you Python code and it's gonna talk to you, and it's the same for it. Like it's just tokens. It doesn't make really the distinction between math and language. So we can use that directly to bridge these two hourglasses. And in particular, what we did is we first used an LLM to break down the different steps that it takes to build a pyramid. So move the gripper above the blue cube, then close the gripper, then move the gripper next to the red cube, then open the gripper, etc. And then we would send each of those steps one by one to another LLM that was able to translate this language into math. And what this LLM would do is it would write us a cost function and the constraints that would go into the controller. So this cost function would come in here and the constraints would come in here. And this is something that the controller can execute, and then the robot can perform the action. So here is what would happen. Then once that action is completed, we would go into the next step, and the next one would be close the gripper. In this case, we would tell ChatGPT there's things that are hard-coded in the robot. So close the gripper would directly be translated into that command, and that is directly passed onto the hardware, and that robot knows that it has to close the gripper. And then we would go into the third step, which is very similar to the first step. And in fact, if you remembered the mathematical formulation, they're actually pretty similar. And that's important because we'll come back to that later. So we again put it into the cost function and the constraints and make the robot execute the action. And in this way, we don't need to know math. We can just talk directly to ChatGPT, and ChatGPT takes care of the math for us. Let me show you different demonstrations. We actually did put this in a robot, and we were able to perform all of these different tasks. So we got the robot to stack cubes, write a letter L, build a pyramid, clean the pan, move a sponge to the sink, and cook the steak. Those last two we only did in simulation because we didn't have a kitchen in the lab. But
Carmen, what was the training set for the LLM?
No training set. That was straight ChatGPT, but we had to prompt it.
Train ChatGPT to translate words into your cost and constraints.
We had to prompt it. Yes.
Okay, but you prompted it, but okay, an LLM requires a lot of words in order to train it to respond. How many of those primitives did you have to train up the LLM on to be able to do the right thing?
I think we tried like 10. I'm gonna show you in a minute.
10?
Yeah. But then we fixed that. Let me finish that, and then I'll get back to your question. Yeah. I wanted to show here the video of the. Yeah. So we actually had recorded a video of the robot. We just told it build a pyramid, and this is what's happening under the hood. So it's saying, oh, remove that. So all what you see there, it's ChatGPT just writing stuff. So it says, oh, I'm going to move the cube, and then it writes it into math, and then the robot's executing it. And then, it eventually managed to build a pyramid. And
what does TP and OD mean? Were those just the
label? Yeah, those are the different modules. So I said, oh, first we break it down. That's the task planner, TP. And that's the one that's just outlining the steps. And then OD is optimization designer, which is the ChatGPT module that's writing it into math.
Thank you.
Yeah.
Excuse me.
Yeah.
How you translate from the image to the mathematics? How you do that? Because you have to have the image about each cube, right?
No, we tell ChatGPT where the cubes are. So there's no vision at all. It's not robust in that sense. No.
Oh.
No. And in fact, we tried that, it was really fragile. We tried like out of the box language caption image modules. We also tried to put in like its own vision module. It was very hard. It's very hard to incorporate vision into this. So it's just hard coding into ChatGPT where the cubes are, and then it just kind of remembers. Yeah. It also got like to clean a pan. So that was cool. And then if you tell it while it's cleaning the pan, if you tell it, oh, you're going too slow, it actually speeds up. It knows what that means. It's like it times time by 2 in the cosine, and then it's able to go faster. So it's receptive to feedback in that way. So yeah, I'm getting to your question, Terry, because here, what I didn't tell you, so I said, oh, I'm building this because I don't want this girl to necessarily need to know math to operate a robot. But I lied, because in order for this to happen, somebody needs to prompt this LLM, give a lot of a few short examples, and those examples look something like this. So you have to say, okay, here's how I would do it. If I was told move the gripper, then I would output something like this, objective, and I have to write this in Python. And this is the kind of thing that we need to turn off. But I wanted to fix this. So let me tell you how architecture helps us to fix this issue and not need this prompting anymore. So I said, well, maybe I don't know math, but I know how to move a robot, right? I know how to perform demonstrations. So I'm gonna just take this robotic arm and do a lot of movements that are gonna be some sort of primitives of that are gonna I'm gonna use to teach the robot later how to label movements. So I'm gonna take this robotic arm and move it on top of the blue cube and label that movement as move on top of the blue cube. I'm gonna do this again, but now I'm gonna have the robot pick up a cube and say, and write in words, this is pick up a cube, like label it. And same thing, like we need like 30 of this. So we need 30 different primitives, but they're very cheap to get, right? Like you don't need to have any sort of expertise, you just move the robot around. And what's interesting about this is that you could say there's an architecture to movement, because how like the movement that you perform could be like the semantic layer. There's this order that needs to happen in order for a movement to be meaningful. We can think of that as syntax, like I need to open the gripper before I move, before I close it, that kind of thing. And then that needs to, like all of that needs to be supported in a way by the little movements that have to happen at the joints. So we can think that there's this architecture of trajectories. And in fact, that's what we collect. When we move the robot, when we have it perform all the movements, we're recording the trajectories, the waypoints that the robot is going through. And so we can think of those as the levels, actually. So we go through waypoints, and that creates trajectories. And this is helpful because in LLMs, we have this. We have an embedding space where the levels are tokens and sequences. And we have this architecture of language that we just discussed. So we have a movement, like pick up the cube, and then we know what that means semantically, and it has a syntax to it. But now we created this thing that we called a feature space. It's not an embedding space, but you can think of it as one. It's a feature space where we have this trajectories, different trajectories that we parameterize. And it also has its own architecture to it, like the layers and the levels that we also just discussed. And so what we could do, do you have a question? Yeah.
Why are we using LLMs in the middle instead of directly giving the commands to the controller?
In language?
Mathematical commands to the controller. What was the reason behind using LLMs?
Well, you want to use language to talk to the robot, like natural language.
Yeah, the purpose is to control the robot.
To control the robot with language. So just to talk to the robot in the same way I talk to my friend. Yeah.
And then we're using another LLM for language to be converted into mathematical.
Yeah, so the reason why you cannot really use one LLM is because it doesn't do as well. So you really need to prompt one LLM to do this train of thought of breaking down a task, and then another one to go from language to math. If you want to do that in one shot with an LLM, it kind of doesn't work. Yeah. So we have this, and then what we can do is we can train a network that it's just this parametric mapping that maps the embedding space to the feature space. So then I say something like, move the gripper above the blue cube, and it knows what that means in the trajectory space. It outputs this parametric mapping, and then I can directly plug this into my cost function. And then that way I can get rid of the few shot examples. Terry, does that answer?
Yeah,
Okay.
except that it can't see blue.
It can't see blue. Yeah, I know. Yeah, it was just like positions. Yeah, I just tried to make
It's
it pretty
numbers.
here,
It's
but
just blue is a bunch of numbers, locations, right?
yeah, exactly. Yeah, hi.
So how do you connect from this space to this space for a general situation that robot has not seen before?
Like, what do you mean?
Like if you go to the last slide.
The previous slide.
Yes, so
Yeah.
you have these two different spaces. So how
Yeah.
do you map like a command from the embedded space to the feature space for a situation that the robot has not seen?
I guess you're asking whether this map generalizes.
Yeah.
Like if we give, so it just does. Like you're learning enough so that when you give a new sequence that it hasn't seen, it just knows it lives in this embedding space, and because you know how to map the embedding space to the feature space, it's able to generalize.
It doesn't work every time.
It doesn't work every time, but it works
Lot.
as much as the prompting the LLM does.
Yeah.
And yeah, of course, I guess this is a good point. The tasks need to be similar enough. So if you're asking the robot to do something that's never done before, like a movement, if the task that you're asking the robot to do involves a movement that it's never done before, then it's not gonna know how to do it. But here, what we're doing is picking and dropping cubes. Like we can break it down into enough primitives that often captures whatever task we want to do. But if you ask to do, like, I don't know, change a bulb or something, which is a movement that it hasn't seen before, I don't know if you'd be able to generalize to that.
The same thing is true for children.
Yeah, I guess. Yeah.
Sure, but how would you demonstrate that this is better than just hard coding this behavior? So you could, instead of going through all these layers of intelligence,
Yeah.
you could just hard code like converting these words and trying to match them in a way. Also, you identify that the blue is not really where it was where I trained, it's over here, and I just match it with the trajectory that I needed to pick up an object from this neighborhood rather than here. So how
So you would, I'm not sure I'm understanding, you would match?
Yes, so you could do this very easily without going through the levels of like intelligence, where you're just matching statements to
math?
to the trajectories, right?
Statements to trajectories.
Yeah.
Well, that's exactly what we're doing here, right?
No, so why do you need the intelligence for that?
What do you
Like,
mean intelligence?
Why do you need ChatGPT for that?
No, we're not using ChatGPT. That's the thing. We got rid of ChatGPT. So if we go back here, we replace ChatGPT. Now this is no longer ChatGPT. This is literally the parametric map that we just needed a much smaller network to learn, and it does not need few shot examples, only demonstrations. Does that answer? Yeah. So this
Also,
whole
you want to just have the human say anything that makes sense. Then you need an LLM to capture the human side.
you need an
You
LLM
need
to
that
break
on the
it
first
down.
one.
The first part you need, because you need some train of thought. You need to break that down enough so that then you can build a map to math. But we were able to, the whole point here was to get rid of the LLM.
So actually what you, I think, have done is automatize the second LLM.
Yeah,
Yeah, and that's what the basal ganglia is.
okay. Oh, interesting.
And the cerebellum, but the basal ganglia is a sequence of actions.
Okay. Yeah. So we wanted to strip down what was the most useful of this, and really with embedding space, turns out you have enough information. You don't need a full-on transformer to do that job for you. You can just learn it with examples. Yeah. So
Great
that was,
question, by the way. Great question. You made her go back and emphasize that. That's really good.
yeah. And also another good thing about this parametric mapping is that it gives us this sort of safety. It doesn't give us a guarantee, but it does give us a metric to assess how far off we are from things that we've seen before. So if I give a new sequence and the parameter that it spits out is very far from all of the other parameters in the feature space, I'm gonna have a metric to assess that, and then I can make decisions based off that. So yeah, and I guess that's another good thing about using control here, is that we can put safety filters here. We can try to add safety to each of these modules, which in my opinion is better than having just a black box LLM. Because if we need to use a robot for something that's safety critical, like having a robot in an operating room or something like that, we definitely want to have this safeguards to account for safety. So yeah, and this, I told you about a robotic arm, but we're also putting this in like drones and cars, and you can think of many different platforms that could go here. And of course, it would be really cool to do this in a distributed way, because then you could have teams of robots and humans and all of that interaction. And I could tell you about how to do distributed control Monday if you want to come to the talk. So yeah, that's it. Yeah, hi. Yeah.
So maybe I'm misunderstanding something, but where's the actual control part? So is the output of the parametric mapping like inclusive of all of the like?
So this is an optimal controller.
Right, but I guess what is the output of the parametric mapping? So
it's the cost function that goes here.
Okay, so that's what's being learned like from the examples.
Yeah, yeah, and we're working on learning the constraints, but that's much harder. But yeah. So now let me tell you about control for language. So we have work in both foundation models and fine-tuning. Sorry, this is all technology, but Rachel sitting there has done a lot for the brain too. So if you're interested in that and control for language and in the brain, you should talk to Rachel. Yeah, so now today I decided to just talk about technologies of foundation models and fine-tuning. For foundation models, it's kind of like pretty heavy math, so I decided not to talk about it today. But here are the two papers. They basically use control theoretical insights and dynamical system insights to understand differences between different backbone architectures like attention state space, RNNs, and also how we can design the architectures inside a layer, the interconnections inside a layer, so that we have guarantees about phenomena such as rank collapse not occurring and so on. So happy to talk about this offline, but now let me tell you about fine-tuning. So how can we use control theory for fine-tuning? So we said the LLM could also be seen as a dynamical system where it has this property, in this case is tokens, and it evolves over time. The token spits out, evolves over time, and it's sort of navigating this we can see the sequence of tokens as like a trajectory in embedding space. And really what's going on is this bow tie where we take sequences, we build we just choose from a reduced pool of tokens, and we keep on building sequences, and the amount of sequences that we can build is like infinitely many. And so in this paper, we used those ideas, and we said, well, we want this building to be controlled. Like we want to work on this control generation for the LLM, and we have a goal, and that goal is minimize toxicity. So we don't want the LLM to spit out toxic content, and we don't want to go in and change the weights, which is what people usually do for fine-tuning. We want to do this directly with a controller. So we want to basically implement this bow tie in this very specific control way, optimal control way. So we designed this controller for the LLM to minimize toxicity. And we did that in a way that was mindful of the hardware implementations, because what you don't want to do is to have this be so slow that then the inference time is just hindered by this controller. So how can you do that like very seamlessly? So that's what we did. So if you take an LLM, it has multiple layers. So you input something, it's a word that gets translated into an embedding space, which is a vector. And then this vector passes through all of these layers up to layer T, and then you get your output. So what we did is for each layer, we trained this classifier that basically told us, we had a label we input something into the LLM, and we know whether it was toxic or non-toxic. And that led us to learning this part of, like a part of the space for each layer that was toxic, that where toxic content tends to accumulate. So we were able to classify for each layers whether an input fell into the toxic region, was likely to be toxic or non-toxic. So each layer had this classifier that we trained for it. And now we can see a layer as, so instead of the sequential view, we can see it as this time varying dynamical system where we take the output of one, we feed it into the other, and it's this sort of closed loop behavior up to layer T. And we said, well, let's put a controller into this. So now we take the output of a layer, and before we feed it into the next layer, we intervene with the controller. Now the controller, it's very similar to the controller we talked about at the beginning. It's an optimal controller too. It's minimizing the size of the intervention. So I'm saying I want an intervention that's as small as possible, but that's guaranteed. If you remember, it was guaranteed to not overflow. Now it's guaranteed to not fall into the toxic region as the classifier. So we compute the optimal intervention. We just add it to the token, and that's what we have. If you don't like this control theory view of learning, you can also think about it where we, in this way, where we just input an intervention to each of the activations in the layers. And
So this version here, you just gave this a recurrent.
I just recurrent
you can do it
nature to
recurrently within the layer.
through the multiple layers.
Oh, okay.
Yeah,
Okay. Oh, so it's the same as
it's the same. It's the same. Yeah. It's just a different view. Yeah. And it would be really cool to think about how to do this in a distributed way for multi-head attention and so on. So the answer turned out to be pretty nice. If we have a specific layer, we just check the classifier. If it fall, and this is some so we solve the optimal control problem analytically, and this is the answer that came out, which is if the activation falls into the toxic region, then we compute this. It's pretty easy to compute. It's algebraic, so it takes like almost no time to compute. And then if it falls into the non-toxic region, you don't do anything. And this is what came out of doing the algebra for the optimal controller. So this respects in a way the laws of the architecture, of the hardware architecture, because the runtime of implementing this is very, very small. So inference time does not really, it's almost not impacted by this. Yeah.
What is the meaning of P in the equation?
Yeah, P is, so you mean this P?
Yeah.
P is a parameter that tells you sort of the tolerance that you're able to accept for toxicity. So whether you want it to be toxic with 30% probability, 0.5 probability, and so it's like the smaller you're making this parameter, the bigger the toxic set becomes, because because it's something is toxic in probability. Yeah. Yeah. And so, sorry. So we have, so this is, I don't know if you can read, but this is an example of the examples that we run. So here you have a prompt that the LLM is fed with, that it says, every Monday we publish the most unbelievable stories. You feed that to the LLM, and for some reason LLMs tend to produce toxic content when they see this prompt. And the whole data set is about that, like innocent prompts that lead to pretty toxic content. And I'm not going to read what it says, but the first one is what happens when you don't have control. The second one is instruction tuning. So this is this was a pretty expensive way of detoxifying LLMs, and it's hard coded, it's fine tuned to not produce toxic content, and it was pretty well. It's like the gold standard for detoxifying. This is us accepting a 0.5% 50% toxicity, so detoxifying at 50%. If you make this parameter really low, then you start getting kind of nonsense generations. And this is some of the state-of-the-art intervention methods. And if you can read, it says something like kindness, 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 kindness. Like it just doesn't produce any language at all. So that's why we drew this plot that's showing toxicity versus naturalness. So the higher you ideally are in this corner, like up there, because that's non-toxic and very natural. You don't want to be here because that's, well, I don't even know if you can, because that is unnatural and very toxic. And so when you don't have any control, when you just let the LLM produce the content, you're in green, which means you're kind of natural, but like pretty toxic. And then this is other state-of-the-art methods. They're just like completely unnatural. The orange is instruction tuning, which is state-of-the-art. And then we are the blue. So for different parameters and different models, and these are different models. So for some models and some values of the parameters, it doesn't work so well. But for the most part, it works similar to instruction tuning, which much less data. We need like 2,000 samples to train, and that's it. And then we don't impact inference time.
What is the naturalness metric for?
We had human annotators just say how natural this sounded to them.
And stepping through of toxicity that was also done by humans.
Yeah.
I was curious if the same approach could be applied to handling hallucinations.
So this is something that I could get into. So we did this for toxicity. We also did this for sentiment. And the good thing about those is that because the architecture of language is like parallel, you can those are specific features that you can test with just looking at a token, because here we're just modifying a token at a time, but often that's enough. Like it's often the case that just one token tells you, or like a few tokens tell you whether something is toxic or non-toxic, positive or negative. It's much harder if you want to check whether something is true, because you have to look at the whole sentence, at the whole context, and that's not an intervention that you can do at the token level. You probably need control, but like in a bigger, like looking across generations, not just a generation at a time, if that makes sense. Yeah, hi.
I was trying to understand how robust this control. So the reason why we are using it is so that it becomes more robust compared to current LLMs, which don't rely on control systems as we studied here. So it's still a software that you're using as a control system in this case, right? And unlike, I mean, the original examples that we studied, which were more electronic in nature.
So I'm not using the controller to make it more robust. I'm using the controller to control the generation to go into the direction that I want. Now it's true that the controller I'm not actuating anything per se. I'm just shifting this vector to be this other vector. So the reason why I'm minimizing the intervention is just to perturb it the minimal possible, not because I'm actuating anything. I don't know if that answers. Okay, yeah.
So along, just to follow up. So one of the things that happens with fine tuning is you dumb down the LLM.
Yeah.
And so that's why you want to reduce the amount of intervention. But
Yeah.
But it sounds like you've minimized the intervention, right?
Yeah, I'm minimizing the intervention.
Oh, okay, so why doesn't everybody do this?
I don't know. I think they should.
Okay.
Yeah. No, in fact, that's my research agenda. I think we should stop fine tuning and building controllers. And
Right.
I really hope for a day when we can go to Hugging Face and download a controller and just plug it in, and that's going to make my LLM now talk to me about medicine or something. You know,
By the way, this is something that also occurs when you're raising a child, right? Children also can do bad things, right? I mean, they can say bad things, they pick up words and so forth. And it's reinforcement learning that helps steer them away from the toxic things, right?
Yeah.
But I wonder if you can relate this to reinforcement learning somehow.
So this is something I'm looking at with reward models, because right now we're training the classifier and that's static. And so whatever you learn to be toxic, then you obey by that. And ideally, you have this big dynamic. So you keep on learning and refining your classifier as you go. Turns out with the current classifier that we've trained, which is the simplest
Oh,
one you
this
can
is
find.
going on during the pre-training?
Yeah, the pre-training you train a classifier and you freeze it.
But this, I thought this is fine tuning you're doing later.
The controller is at the fine tuning, is instead of fine tuning, you're using the controller.
Oh, I see. This
Yeah.
is during the actual
During
initial
inference.
training.
So you train, no, you train the LLM, the LLM's
Okay,
training.
so it's pre-trained, okay,
Yeah, now you train a classifier
okay.
and you use the classifier to put it as the constraints of your controller.
Oh, I see. This is like an add-on, like this, like, in
Yeah.
other words, it's doing it like what fine tuning was supposed to do, but it's doing it better by
Yes.
intervening in a
Exactly.
different way.
Exactly,
Or
yeah,
not intervene.
yeah,
Well, adding this little
Yeah.
Not having it,
perturbation,
or
or
otherwise,
adding a
yeah,
perturbation at every level.
yeah,
To make minimal changes at each level, but that the output is going to be guaranteed.
yeah,
So-
yeah, exactly. And so you could change, you could imagine how the controller learns what's toxic and what's non-toxic on the fly, which we don't do yet. And also you can have it change controllers. Like now you don't want it to be toxic and now you want it to do something else. So you don't need to use the fine-tuned LLM for the specific task. You just change your controller.
Okay, so actually this raises the possibility of having a whole set of controllers.
Yeah, where it
Where-
learns what
where
it
each
needs
one
to do.
learns a different type of toxicity, or like in a,
Yeah.
well, first of all, toxicity means a lot of things. So for example, you may want it to be not to give away methods for biological warfare, right? For creating
Yeah,
toxic, but this is real toxic, viruses, right?
yeah,
So that would be different from the controller for keeping it from saying bad words.
exactly. Yeah, yeah, for instance, yeah. Or you would activate some constraints or some others.
Right.
And you could have it ideally choose its own controllers. Like say, oh, context changed, so
Oh,
let me
that's
change my
interesting. So
controller.
it could learn to, I see, it could
Yeah.
actually learn which controller to use.
Yeah, it's almost like it could fine tune itself, only you're not touching the weights. You're using the, yeah. Hi.
Yeah, just a question for you back. So, along the lines of that same, it'll be interesting to see which sites in the model intervention works best. So, you probably have a transformer network in there, and you're trying to control certain regions.
Yeah.
So maybe something you've done already. It's a question of what is the impact of your site of intervention on overall performance. If you choose to intervene closer to the token inputs versus midway closer to.
Oh, I see. Yes, yes. Yeah, that's a really good question. So at the beginning, when we started doing this work, we trained and we said, oh, we trained the classifier, and there is some, I think it was layer 16, captures most of the toxicity. So we said, so with 80% accuracy or something, you can determine whether the output is going to be toxic or not at layer 16. So we said, let's just intervene layer 16. Turns out that the intervention has to be much bigger. It perturbs the output a lot, the activation a lot, and it's just not enough. So it's just much better to intervene every layer. It's very cheap because, as you saw, the computation is very cheap, and then it just, yeah. So this idea of like you control over time. Like I always think, like if you're a car, you don't want to brake at the last minute. You want to start braking early enough. So this is kind of the same thing. You start doing it. You start dumping it down at the beginning of the layer, so that when you get to the end.
But even on the multi-site intervention approach, right, how some sites would be still more sensitive than others. Right? So you could create some sensitivity analysis of layer intervention and ultimate result that you see. Right? So
Yeah.
you have a distribution of sensitivity of intervention. Does that make sense?
Yeah, but I think that would be like application dependent in a way. Yeah, like for toxicity you might find something, and for sentiment you might find something else. Yeah. Hi. Oh, sorry.
So, great presentation so far. So my question is, what's your benchmark for both tasks you introduce, language to control and control for language? So, I mean, for language to control your robots, I mean, you can tune, everyone can tune their own prompts, and I mean, maybe your prompts may achieve very efficient or effective results in controlling robots, and for control for languages test, the algorithm, the control algorithms you choose for to reduce the toxic of language shows efficiency. But I mean, every work, I mean, I suppose in the future there will be more and more work similar to yours, use ChatGPT to perform two tasks, and might be everyone will claim, oh, my approach is better and is effective. So my question is, do you have or have used any compared with your method to any of the benchmarks so far, or in your work? I mean, it's like a baseline or like ImageNet in image classification or segmentation, other traditional computer vision tests. So is there any benchmark you set up for your work so far?
Yes. So in fact, for this one, we compared with this, which is state of the art. So these are methods that are state of the art for intervening LLMs, and we're benchmarking against them. And in this plot, I haven't included all of them, but we've been benchmarked among all of the methods, like many methods for control generation in LLMs. We also benchmarked in robotics. There is different methods for how to talk to your robot. We also benchmarked against them. And yeah, every work we do, we benchmark with whatever is state of the art. And it's always like we always like our own part or be state of the art in some way. In the works that I've presented.
So you have a bunch of different LLMs. There are Llama, Mistral. Those are open source, right?
Yeah.
Okay. Which has turned out to be the best to work with?
So we don't do so well with Mistral for some reason. Mistral is not as good. Llama, I think Llama is the one that's most widely available. But I think for sentiment, there was a small delta between them. For sentiment, we were finding like slightly different results. So I don't think that I could tell you which one is like the absolute best. Yeah. Hi.
Thanks for the great talk. You talked about a lot of.
Wait. I don't think it's done.
Yeah, I know. Well, I'm almost done. Right? Should I finish? Okay, I'm almost done.
Okay.
I just wanted to say, like a summary. This is all enabled by this view of architecture, So this idea is really. Although the works stand alone by themselves, and if you read the papers, those ideas of architecture are not explicitly stated there. They're very inspiring in making all of this possible, and this is really what connects all of the works together. And I think that's all I have. Thank you so much. What?
So yesterday I gave you a whole bunch of examples of these universal layer. Actually, I didn't give you very many, but I could have gone to bacteria. So I have an infinite list of examples of this universal layer architecture. Language is the cleanest because the layers and levels are all the same. The bow ties and hourglasses are all the same. In Terry's picture, going down to molecules, every level has a layered architecture inside it, but they're all different. And also, you got to go to the microscope. There's no microscopic stuff here, right? It ends at tokens. So it's this really elegant application of theory. Like, had I known this, I said, "Dog, I don't work on linguistics." I'm such an idiot because, of course, she knows I'm an idiot, and so she went ahead and did it anyway. But had I known that this was going to be the example that really best illustrated it, and plus everybody does it, so you don't need to know like biochemistry to understand this picture. You just. So I can't tell you how glad I am that she didn't listen to me. Anyway.
Does that mean the brain is inefficient?
Why?
Okay, thank you. Talk, but there's something that you left out. Wally. Okay. So, she had the phonetics, which is the sound of the letters, and then you know the syntax, you know, or the orders of the words, and then meaning. But it was left out as intonation, emphasis, and you know this is a way that you communicate not just meaning, but the value of the meaning. Or
yeah.
That was a double positive. Okay, but in any case, questions. Let's go back. You had a question. Why don't you ask?
Yeah. So one of the things that I think I know you have to get through so much, but it's really cool. It's just like how quickly your model was able to learn from expert demonstrations. And I was wondering if this is like currently commonly being done for like, I don't know, like you want to learn the control law for a human moving their hand to grab an object. It seems like it would be very reasonable to like have something attached to your hand to do something very similar. Is that much harder than the application?
So we're using, it's multitask control, which is its own subfield. And the what we're using there is the fact that the movements are similar and they're parameterized with this one parameter that lives in this feature space or like this set of features. And then we're really learning the feature. So you're parameterizing something. So basically you're assuming some structure in the movement. So that's why it mattered when I said, oh, look, these two tasks, they have very similar representation. That's key. If they didn't, and they didn't have a shared structure, then you're done. So yeah, maybe for the hand, it's like a little bit too complex. I'm not sure.
And that parameter is that row that you have?
The row, yeah. And that there's much more detail in the paper if you're interested. Yeah.
So you just mentioned, you know, the simplicity of language in terms of in the view of this universal layer architecture. And I've seen some papers that also try to mention, you know, like the success of transformers on language is kind of because it's like an innately discrete domain that is like very information dense compared to something like images or videos, which has a lot of, it's continuous and has a lot of noise and everything, and has a lot more complexity in it in terms of the interaction. If it does follow this universal layer architecture, it has a lot more complexity. And so for those other domains, what should we do? Should we attempt to tokenize everything so that they try to, you know?
Well, if I knew the answer to that question, I probably would be rich. Yeah, I'm not sure, but I do want to point out that I don't think it's a discrete nature. People talk a lot about discrete versus continuous. I think the key is the parallel architecture. So the fact that you have semantics both and tokens and in sequences. And that's really what allows you to detoxify just by looking at the token. So that I think that the reason why you're able to build those meaningful sequences from tokens is because they share this parallel architecture, which I don't think is true in other domains. So that's my conjecture. I don't think that's true. Like I don't think it has to do necessarily with discrete versus continuous, but that's my opinion.
I just want to say one thing about that. So the way you would think about doing vision and how our brain actually does it is not how machines do it now at all. And so it's conceivable by rethinking vision from both how we do it, really, which has only recently been understood, and how you should theoretically do it, which happen to be the same. You might rethink how you do vision completely. Now, nobody's done that yet. Like, just nobody rethought. This is a complete rethinking of language from the ground up. And so somebody has to just do that. I don't know. I don't know what the answer is. I thought this was, so I was wrong. So anything I say about it will be wrong. And so do the opposite of what I would conjecture, but I just won't conjecture because anyway. But I think, that's a great question, which is, are there other ULAs out there that we haven't really recognized? And we know vision in our brains has been completely misunderstood forever. And in practice, Ann Churchland just showed how it works with, experimentally. And it's completely consistent with what our theory says it must work. But that's not how our computers do it. So could we do that? I don't know. But it would be interesting to get someone in computer vision to actually try that. But that would be true of a lot of problems that I would think, oh, no hope, and then yeah, no, that's our theory.
So one way of thinking about this is that we have now way of looking at problems that are completely different from the way it was done early days of AI. In other words, looking at the architecture of a problem, seeing how to map it into a particular structure where you have levels and layers, and this, you know, that's going to tell us, I think, how the brain ultimately was evolved and solves all these problems. But it really, it is a conceptual framework that is not natural. That is to say, it's, well, not in the sense of, it is natural because obviously it's in nature, but it's not natural for us to think in terms of this architecture. It's so new. It's just like, you know, you might as well start from scratch, right? I mean, and what this means is that you're going to get a lot of blowback from the traditional way of thinking.
Oh yeah.
Yeah. No, this is the reality for the young people out there. You have no idea how much blowback we were getting in the 80s when we started working on neural networks by the experts. I mean, these are the experts in statistics, in optimization theory, in AI, and this is now, we're going to go through the same thing.
By the way, the control theory she's talking about on Monday got huge blowback initially, like including from me, like this can't be right, kind of stuff. And then the students explain it to me, and I go, okay, yeah, it's right. And then the reviewers, this can't be right. But that lasted about 6 months, and then it just won every award that it was eligible. So in that case, the reason that was so short is this is people who are both engineers and care about not killing people, and they're mathematicians and they care about rigor. It was this unique community, and they will just thrash you and then go, oh yeah, sorry, you're right, we're going to use it now, right? The problem is, you get really spoiled if that's what you're used to.
Yeah, well, right. I can tell you that in science, it's not that
it's
easy.
Not. Oh boy. Oh, I can tell you in science, it's not like that at all. Like physics. Oh my God. So anyway, yeah.
Okay. Well,
the hope.
We can only
Anyway,
take a few more questions. Okay, go ahead with that and Gert. Okay, good.
So I had a question about the toxicity detection and the intervention at the different layers.
Yeah.
So you said that you were tweaking this manually, but do you see yourself optimizing these interventions and these probability variables using maybe another LLM or maybe another optimization model to tweak it to different contexts?
Oh, you mean that I'm tweaking manually the intervention to the context?
Yes, for the different layers.
Like the p-value.
So, the p-value.
So you were saying that first you tried to tweak it just to have it at layer 16, and then you were saying that, oh, maybe the earlier layers need a bigger intervention.
Yeah, so I'm not tweaking it, like, I'm just letting, like, it's automatic, the intervention is computed automatically.
Okay.
At every layer. So what's happening is that this, whether the activation falls into this region, this I need to train beforehand. So this is the different contexts. And this, yeah, ideally, we are able to build controllers that are able to detect what the user wants, kind of reading between the lines, and then adjust what region that would be that they need to avoid. Yeah, so that we're trying to do that with our war model.
But you varied P.
I vary P. Also with the experiment.
You know, that's a variable, right? It's not something that's fixed by the controller, is it?
Right, that's something that you choose.
You choose, okay.
Yeah. And that's based on the natural.
Well, wait a second. No.
I'm sorry.
Gert was first. Okay, go ahead.
Sorry.
Answer your question.
Yes.
Okay, Gert.
Actually, this is very beautiful. I love it. It's great. So in machine learning, right, or for natural language processing or not, sparsity is very important, right? Typically, we use models, large margin models that have sparsity in them, right?
Yeah.
And so now it looks like you have this element of sparsity in control, where the best control seems to be knowing when not to control, when not to intervene.
Yeah.
Right?
Yeah.
And so that's great. Same with parenthood, right? You know when to
Yeah.
let the children do, right? And you know when to intervene.
Yeah.
Yeah, yeah. So this came
So
out.
is that, I mean, can you indeed have the P parameter as a control of sparsity in your
Yeah, P, you could like hyper optimize for P or something. But then it affects your naturalness, and I don't really have a way of measuring naturalness if it's not a human annotator looking at the output, so that's kind of the issue there. But yeah, this idea of you only intervene when you're in trouble came out of the controller formulation that was, well, whatever, like this formulation that it's the optimal control that just says, please be as small as possible, guaranteeing that I don't fall into the toxic region. And then it all comes naturally from that.
Go layer by layer, you do in this way?
You do this at every layer. So at every layer, you're computing this.
But how you know that the global is minimum?
It might not. That's true, because it's a relaxation. We're removing the dynamics from the picture in order to solve a closed form. So it might not be optimal globally. However, optimality globally just means this is as small as possible. I'm okay with that. I'm okay with having the intervention be slightly bigger, if that lets me compute this closed form and then be efficient.
But the minimum there is depend on the other layers, right? And then when you obtain the minimum of this value, depend on the other layers, because you fit the before layers.
Yes, but I'm doing a greedy
then
approach.
When you remove, you optimize the next layer, you change the response